A machine learning model assumes its training data is a pure, untouched resource until the surface is disturbed by the reality of the source. This diagram shows a standard machine learning feature table. On the surface, it appears completely structured, with unique user IDs aligned perfectly against total spending metrics. But underneath lies the raw source data, where human error fractures single identities into dozens of disjointed rows. A user might type their name with a slight variation, switch to a new phone number, or abandon an old email address when signing up across different platforms. Data engineers typically attempt to clean this up using exact matching commands, like Spark's drop duplicates function, to find and merge identical rows. That approach fails against real-world data entropy. If a user inputs John on mobile and John on desktop, an exact match operation treats them as two completely separate individuals. This creates latent duplicates that flow directly into your feature engineering. The spending metrics for one actual person get double counted or split unevenly across multiple ghost profiles. When you feed those inflated metrics into a predictive model, the algorithm overfits on the redundant noise. It learns to predict outcomes based on duplicate artifacts rather than true user behavior. To accurately resolve these fuzzy identities, we have to stop treating data as isolated rows in a table and start treating it as a distributed mathematical graph. Imagine a massive, unstructured data pool containing millions of fragmented user records waiting to be analyzed. Before we can begin deduplicating this data, we need a strict mathematical definition of string similarity. We use Pyspark's native Levenshtein function. This provides the exact metric required to calculate the edit distance between any two strings. Edit distance calculates the minimum number of character changes required to make two strings identical. Adding an H to John to make it John equals a Levenshtein distance of exactly 1. But applying this calculation across a massive dataset creates a combinatorial explosion. Comparing every row against every other row creates a scaling crisis that will crash distributed memory. To solve this, the Pyspark function includes the threshold parameter. This acts as a strict numerical limit on the calculation itself. If the algorithm detects that two strings are too disparate to meet the threshold, it halts the similarity calculation early. This discards the pairing and saves massive amounts of compute resources. The distance scores that survive this cutoff provide the quantitative relationships needed to build out a spatial network. By mathematically bounding the similarity metric, we can safely compute relationships at scale without crashing the cluster. Relational data frames are structurally flawed for mapping complex, interconnected identity variations. To map these identities, we use the Spark Graph Frames library to project flat data into a network topology. First, we project tabular records into standalone nodes, floating in a spatial graph. Without defining relationships across the empty space, these isolated nodes lack structure. We draw edges to generate relationships, but only if the Levenshtein distance between nodes falls below the threshold. This conditional edge links non-exact records, drawing a direct path between a misspelled name and an old email for the same person. Scaling this rule across millions of records transforms the dataset from a rigid list into an interconnected web. By traversing these drawn edges, the system can algorithmically walk through the human entropy of typos and account changes to see how identities actually relate. This graph topology naturally maps the real-world fuzziness of human identity far better than rigid relational tables. Having built a massive web of nodes and edges, we must now isolate the individual human identities hidden within it. We do this by applying the graph-based connected components algorithm to segment the web. The algorithm traverses the graph to find completely isolated subgraphs. It looks for clusters of nodes that share edges with each other, but share zero edges with the rest of the network. Each of these isolated subgraphs definitively represents a single true user entity, grouping all of the slight variations tied to that person. But algorithmically grouping these nodes is not the same as merging them for the final feature table. We must implement record selection logic to determine which node becomes the canonical source of truth. We look at metadata attached to each node, specifically the sign-up timestamp. A window function isolates the record with the maximum timestamp, discarding older nodes. applying connected components and window functions, collapses noisy subgraphs into the single high-fidelity records required for accurate ML training. This diagram shows the complete end-to-end data pipeline, tracing the path from raw entropy through to the clean output. Because this architecture is built natively in Spark, the heavy graph computations scale seamlessly across distributed worker nodes. The clean output splits into two distinct paths, sending accurate entity counts to business analytics and clean feature matrices to ML pipelines. Training on deduplicated data reduces model noise by ensuring that individual user signals aren't fragmented across redundant profiles. While graph segmentations often run in batch, the same logic can be adapted for live environments by comparing incoming records against a stateful store of historical nodes. Using Spark streaming, we can apply the Levenshtein threshold to incoming data points continuously, merging them into existing identity clusters as they arrive. This continuous deduplication is what enables high-stakes applications like live fraud detection to maintain accurate user histories even when account details shift in real time. Graph-based entity resolution replaces manual, brittle rules with a scalable mathematical framework, ensuring that the data used by production models accurately reflects the entities it aims to predict.